You are given an array and you can split it into as many consecutive blocks as you like. And once you have split the array into several consecutive blocks, for each block, you find out what is the frequency, what is the maximum frequency of any element inside this block. So if an element appears 3 times and no other element appears more than 3 times, then the contribution of this block will be equal to 3. So you count this, you find out this number for each of the colored blocks that you see on the screen and you add them up. So that will be the value of the split. So value of the split is the, for each block you compute what is the maximum frequency of any integer inside that block and you sum that up to get the value of the entire split that you have made. You can see that there are multiple ways to split it into consecutive blocks. So your goal is to find out if you can make this contribution of all the blocks equal to an integer k that is given to you. How do you solve this problem? Take a minute to pause this video and think through how you would approach it, because as per me, the solution is definitely not trivial, even though the code might be. Now let's talk about how you would approach it. So this video is all about making some sharp observation that will help us simplify things. So one thing you can notice that the first observation that you can make, let me write that down as observation 1, is that since the contribution of a split, since the value of a split is equal to the sum of maximum frequency, and you should know that this is a very common trick used in competitive programming, that whenever you are trying to sum up frequencies, then you can say that the total sum of the frequency of this block and this block and this block, etc., when you add them all up, they cannot exceed the length of the array, because frequency means that many, if the frequency is x, then this means that x copies are present, this means that x slots are already occupied, and if this frequency is y, then y slots are already occupied. This means that the total frequency cannot exceed n. And this is one of, this might seem very trivial observation for this problem, but believe me when I say that in a lot of 1800 and 1900 rated problems, this fact is used. That is, when you try to apply an algorithm, you have to keep in mind that the sum of frequency cannot exceed the total number of elements in the array. So this is the first observation that you can make. And if the problem says that k is greater than n, you simply respond no, that there is no split that can achieve that value k that you are looking for. But then assume that the problem specifies that k is less than or equal to n. In that case, how do you solve it? So to solve this version, again, you can try to brainstorm some ideas by pausing this video and try to think through the solutions. One obvious strategy that comes to mind is that let's focus on this last element. Either it will get its own block, or it will be in a block that combines with this last second element, or it will be in a block that is combined with the last third element. These three elements will form a single block, and so on. Then you can notice that this is a typical dynamic programming problem, because there are n different possibilities for the last element to form a block. It can either form it alone, or it can form with the second element combined, or with the last third element combined, these three elements, and so on. So assume that you decide on this possibility. So you have to explore all the possibility, but when you are exploring for this particular possibility, you are now interested in what are the different possible sums that you can contribute, that you can achieve by splitting this section, and then you find out what is the contribution of this block. So this would be easy to maintain in a map, since you are iterating from right to left and you are only adding elements to the map, so you can keep track of the maximum frequency. So you know the contribution of this block, and once you decide to make a cut over here, you are now interested in finding out how many distinct k values can this cut produce. So you actually have to store all the possible distinct k values. So you will define something like this: dp of I k. This means that from the first I elements, is it possible to cut them so that the blocks overall blocks contribution, that is the sum of max frequency of each cut, is equal to k. And how do you do the dp transitions? So once you do this cut over here, you can see that for this cut you have to iterate over all the dp values of this prefix which says yes, and then you have to update the dp value of k plus whatever this number comes out to be, whatever the contribution of the last block. Suppose that is x, so you have to update dp of k plus x, where the first index would be the element that has just entered the set. So of course this would work, but then the time complexity would be O of n square. And you can see that there is no easy way to optimize this dp. So what you need to solve this problem is some out of the box thinking, and you need to make some observations so that dp is not needed in this problem, and you can come up with other strategies to do this. Because if you haven't realized, the first observation that you made by itself, it wasn't trivial at all. Why the answer will be no if k is greater than n. So we have to make a series of similar observations. So let's start by making the second observation, which is observation 2. In this second observation, when in these kind of problems, since you want to focus on the maximum frequency of any element in one of the blocks, so since you are not able to make any progress with dp, you might consider focusing on the original array, and let's locate what is the maximal frequency element. Suppose it is located here, here and here. Now you can notice that if you do not make any cut, then your answer is equal to 4, because what is the frequency of the maximum element? What is the maximal frequency of any element? That is equal to 4. And since there is only one block, so you don't have to sum it up anymore. So the answer is 4. So only 4. If k is equal to 4, of course the answer is yes. Now let's see what other values can we obviously achieve. Like with very simple strategies, what other values can we obviously achieve, or what other values are impossible to achieve. So first of all, let's talk about the cases that are impossible to achieve, because this might be an easy way. Because we have already seen that k is greater than n is impossible to achieve, and the arguments for that were pretty solid. So looking at this, can we find out some k that are definitely impossible to achieve? So you can notice that if you let all of these copies of x remain in the same window, they will contribute at least 4 in that window, in that block, and your answer will be 4 plus delta. So your answer will be definitely greater than or equal to 4. So if you really want to go below 4, if you want to go down, then you definitely have to split this x. So you have to split it into a different block. Now this is where we make the second observation, that watch what happens when you do this split. So you will of course have to separate out this x from this group. So once you do the separation, notice that if these elements, if they remain in the same window, they will now contribute 3. But wherever this x went, this will still compete. So you can say that in whichever block this x is present, it will still compete for the maximum frequency, because in whichever block it is present, its frequency is 1. So since it will compete, either it will win and then the block's contribution would be 1, or it will lose and then the block's contribution would be greater than 1. So even after making this cut over here, you can see that since it is competing for the maximum frequency, even if it is not part of this group over here, it will still contribute 1. And since they are part of that same block, they will contribute 3. So you see that they still produce 4. So this means just isolating one x is not good enough. You have to isolate more x, as many as possible, so that they don't add up. Because see, the maximum contribution is coming from this side. These are combining together to produce 3. So let's try to isolate them even further and then see what happens. So then you can see, you can try a split something like this. You say that okay, you will not let any of the x remain in its own box, remain in the same box. So you will make a cut over here, you'll make a cut over here, you'll make a cut over here, and you'll make a cut over here. Then notice what happens. Even when you have isolated all the x's, each of the x will compete in its own block, and the total number of blocks that you will have to create to isolate each x will be equal to the maximum, which will be equal to the frequency of the uh, most natural, will be equal to the frequency of x, which is the element that appears most number of times. So you will have to create 4 blocks at the very least, and in each of these 4 blocks, x will compete for the maxima. In fact, you can view it like so. So if it is x, so in place of x, what you do is everywhere. So in the original array, we had written x, right? X over here and x over here, x over here and x over here. So you can in fact replace this array with a binary array, and you add 1 everywhere x is present, and you add a 0 at other locations. Then you can see that if all of the x's are part of the same window, then they are adding up their contribution, and they are collaborating, and then they are producing the answer as 4. But even if you bring only these two x in this window and then these two x remain in this window, even then they are adding up their contribution and it is becoming 2, and they are adding up their contribution and it is becoming 2. And if you isolate them in their own windows like so, then even in their own window they will contribute at least 1. So you can see that you cannot get rid of this ones, because all the other elements are 0, they are not -1. So we are assuming that none of the other elements are competing. So now it is clear that your answer has to be greater than or equal to the frequency of x, right? Where we are assuming x to be the element with the maximal frequency. So this was observation 2. Now for some of you this might be obvious, but for others this might not be obvious. So now we are going somewhere. You can see that with DP we were kind of stuck, no obvious optimization to do. But with this, you can see that our strategy of isolating the X didn't really work out for us, because no matter where X is, it will add its contribution. So now suppose X is present over here, over here, over here, and over here. So we know that it is definitely possible to achieve K is equal to 4, right? You just take the entire window, and the element with the maximal frequency is X and the maximal frequency is 4, so you will get 4. Now we will make another observation. So this is now observation 3. So observation 1 was that K greater than is equal, K greater than N is false. Observation 2 was that and this stemmed out of the fact that the sum of the frequency cannot exceed the total number of element. And observation 2 was that all of these elements, they combine their power. So even if you keep them in the same box, they will combine their power, but even if you isolate them in different boxes, their contribution will still be combined, because you are using this sum function over here. So now let's talk about observation 3. And in observation 3, we are saying that, okay, if it is so K is equal to 4 is definitely possible. Now can you do a smart construction and figure out at least one K that should also be possible? And I don't really have a good justification for this, because this kind of intuition you can only build by solving a lot of these kind of problems. So that's why I have uploaded a video on this. And that intuition is simply, a lot of you I believe must have already found it, is that you can give this element its own block. You can cut a block over here, you can give this element its own block over here, and you can keep the remaining window like so. So we know that even if you shrink the window, since all your copies of X's are available inside the window, this block will still contribute 4. And since this element got its own block, it will contribute at least 1, because this element will compete. So you can see that K is equal to 5 is also possible. In fact, you can also see that K is equal to 6 is also possible. How? You can give this element its own block, and you can have all the copies of X inside this block. This is also not hard to observe. In fact, you can notice that K is equal to 7 is also achievable. This might be a bit tricky, but not that tricky. How is this achievable? You just have to look at it from the different angle. So you can say that this time you still keep this block over here, but you give this block to this element alone. So this will contribute 1, and since all the copies of X's are in a single window, they will contribute 4. So K is equal to 7 is also possible. So now we know for sure what is definitely possible, what is definitely not possible, and what is in the range maybe, like what could be possible and could not be possible, right? So we have seen that if this is 0, and if this is f of x, where I am assuming f of x is equal to the frequency of the max, f of x is equal to the maximal frequency, and this is n. So we know for sure that this region is not possible, because each x, no matter where it is, it will compete for the maximal frequency, and from here to here some region is definitely possible. How can you do that? You can do that by giving each element its own block in the prefix as well as the suffix. Now if you are watching this video, most likely so far you have already come to this conclusion, right? The real challenge arrives in knowing what all values can you really achieve in this window, because with this construction you are smartly able to give each element its own block. But now when you separate out the x, you will start seeing issues. So now let's try to make the next set of observations, which will be a bit far-fetched. I'm already warning you ahead, but maybe not for some of you. For some of you it might be pretty intuitive, but let's see. So this is your x, this is one copy, this is the second copy, third copy, and let's say this is the last copy over here. And without loss of generality, we can just assume that x's lie on the suffix, and we have tried our best we can on the prefix. We have given each of these elements its separate box. And then we want to wonder about what happens when you do that same trick over here. Now notice that if you have given each of these element its separate box, then your answer would be equal to what? If this is equal to k, let's assume that the maximal frequency is equal to f. Let's define it as f. Instead of f of x, let us call it as f. Then you can see that you're right now, when you have done this split, you have given this element its own block, this element its own block, and this element its own block. Then your then your answer at that point is f plus 3. Now if you try to apply that same trick by giving this element its own block, now notice what happens. Then sure, you have increased this 3 to 3 plus 1, right? But then at first glance it looks like that you have stolen one x from the window, right? You have stolen one x from the window. So now the contribution should be of this window should be equal to f minus 1, and the contribution should not change. So this is what it looks like at first glance, but actually this is incorrect, because what is the guarantee that there are no, so remember every time we were talking about maximal frequency, not the maximum frequency, because more than one element can have the same maximal frequency. So what if when x leaves this window, we know that any element cannot have frequency more than 4. But what if this window had been long, and what if y competed here? Like what if once x was out of this window in this range, what if there were 4 copies of y still available, but since x and y were identical at the start, you did not pick y as your candidate, you picked x. But now that x is out of this window, in this window y could still win. So if you are lucky, that is exactly what would happen, that once x leaves the window, y will take over, and this will actually not reduce to f minus 1, right? It will actually be equal to f, because y has taken over, and then you can see that f plus 4 is also possible. Okay, but what if you do get unlucky? That is, what if your x is evicted from the window and nobody is present in the window to take control? That is, your window now only has 3 element, that competes for the maximal thing. So you can see that your old was f plus 3 and even your new would be f minus 1 plus 3 plus 1, and this would cancel out. So you still are stuck at f plus 3 only. So now with this in mind, you can see that not everything is achievable. So if you are over here, so you know that if you locate the window, the minimal window that contains all the copies of x, then suppose the maximum number of copies is equal to f. So you know that you can achieve f plus this prefix length plus this suffix length comfortably, right? F plus p plus s. And on a number line, this looks something like this. This is f. So all the smaller elements you cannot achieve, and some prefix you can achieve, which is f plus p plus s. And from here, things start getting tricky, because when you try to give each element its own block, then x could be evicted from the window and nobody will be there to take control. So you lost an opportunity to increase this f, right? Now, and then this process can even continue, right? In fact, the next element that you remove from the window, it could still be another copy of x. Now let's explore the case where somebody is actually there to take over. So assume that you have this window and this is the first copy of x and this is the last copy of x. So assume that you are cutting the window like so. Then if an element is actually taking over, then if the previous value before this cut, that is in this bigger window, this previous value, if this value was equal to m, then once you make the cut, you see that one element has gotten its own block, so it will increase by 1 provided that somebody is there to take charge inside this window. So suppose y will take charge and y is present over here, and over here. So 4 copies of y are still present, just like we had 4 copies of x inside this window. Now you can see that now you are actually more lucky than you think, because now you can move your pivot to this y and this y. And since this y is your maximal element, now you can freely cut elements in its own block. And every time it is guaranteed to increase. Why? Because it is the same situation as this x. So you can see that you get a lot of leeway if your maxima candidate changes, because you can actually trim this prefix and you can trim this suffix. So as long as your maxima, if as long as somebody is there to take care of your maxima, then you are good. But then sometimes you will miss your maxima, right? And then your m might not change, and it might not change for a long period of time. So suppose if this is x, then if this is your m, then it might not change for a long period of time. But here's the crazy idea. Okay, now all of this would make sense in hindsight, maybe, because maybe I'm explaining it in such a way that a lot of you might have already figured out what's going to happen. But here's the crazy idea. So you say that, okay, sometimes you get lucky, sometimes you are unlucky, but what you do is you be persistent, you keep on doing the hard work, you keep on making the cuts. So you have already made all the cuts in the suffix and you have provided them their own block, and you have already made the cuts in the prefix, you have provided them their own block, and you are only worried when you are making the cuts, and you are worried that, okay, if you cut an x and nobody is there to take charge of this window, then your m will not change. but that's fine, you still make the cut. So there are only two things that could happen. Either your m will not change, so you will stay at m, or it will increase by 1, right? Because if you are lucky, it will increase by 1 because some other element is there to take charge inside that window. Now notice that if you are persistent and if you keep on making all the cuts, what will happen at the end? At the end, all the elements are in its own block. So naturally, every element will contribute 1, right? Every element will contribute 1. So when every element contributes 1, you have achieved the value of n, which lies over here. And you started doubting yourself when you were standing over here. This is f plus p plus s, right? This is the prefix plus suffix endpoint we were talking about. And now here is the crazy idea that if you did reach n and you started from here, then it is guaranteed that sometimes you might lose, sometimes you might win, but every time you win, you can only win by 1 step. But if you lose, you stay there. So since you eventually reached n, you must have definitely crossed each and every element on your journey to n. And this actually solved the problem. So this was the crazy idea that I was talking about, because if you look at it just from proof of correctness perspective, there is no doubt about it. And in fact, I wouldn't say that this kind of reasoning is very new. I have seen it in other problems as well, where you claim that if you start at x and you eventually reach y, then you must cross everything in between. So if you are an experienced competitive programmer, where is in which algorithm have you seen this pattern where we use this fact that if you start at x and then you reach y, then the number of operations that you do is something so and so. So if you remember, if you have seen this algorithm called LPS, longest prefix, which is also a suffix, which is also known as the KMP algorithm, right? In this algorithm, we use this fact that in every time uh, your pi function increases by 1, and then it can decrease by any amount delta, but since it can only increase by 1, so the total work done is O of n. In fact, we make this same argument in your stack based problem. So a lot of problems that deal with stack, right? For example, computing the next greater element and so on, we make the same argument that since even though you have a while loop inside a while loop in stack based problem, we claim that the time complexity is not O of n square, because every element will be pushed onto the stack once, therefore it can only be popped once. So therefore the total operations is O of n and not O of n square. So we are making the same claim over here, that since you started at this point and eventually you are over here, this means that you must have crossed every element in between, because your m could have either remained the same, and if it had remained the same, then there was no way for you to eventually arrive at this n, or it would have increased just by 1. So you can see that the answer to this complicated problem is just if k belongs to this interval f to n, your answer is yes, otherwise the answer is no. Now, of course, some of you might find it like still a bit magical, right? Like, okay, the proof of correctness works, and with this kind of like arguments that we are making, and of course these arguments are true, but then how would you have even guessed about this, and like what is exactly the intuition behind it? So in the remaining part of this video, I'll quickly talk about the intuition behind it. But what is important to still learn is that even if you don't have the intuition, maybe this is a good skill to develop, like making these arguments that you reached from here to here, so you must have crossed every value in between. So I think that's a beautiful observation nonetheless. So now let's talk about the intuition behind it. Like if you did not make this argument, can you intuitively show me how every value is actually achievable when you are making these cuts? So let's look at that at the in the last segment. So I told you that every time you cut a copy of X, suppose you cut this copy of X, and if an element is there to take charge, suppose multiple copies of Y's, they succeed X, that is, 4 copies of Y's are still present, so that even if you cut one copy of X, it's no big deal. This means that you will not have any problem in this entire journey because no copy of Y is being cut. So now let us only talk about the case. This means that you will only get unlucky. When would you get unlucky? So every time you get unlucky, something unique happens. And that is what proves the correctness for the solution. Something interesting happens. And what is that interesting thing? Every time you make a cut and nobody is there to replace it. So if you have this big array, and suppose you make a cut over here, this is X. This means that you have just removed X from this window, but your sum of contribution of all the blocks, it is not changing. This means that in this smaller window, nobody is there to compete with X. So if the older maximal frequency of X was 4, then after removing one copy of X, if the frequency being contributed is 3, you can make some strong deductions from this. What is that deduction? That deduction is that every element that is remaining has frequency less than or equal to 3. So this is the first time that you got unlucky, where you made one cut. Now we can assume that the second time you will get lucky, and then the third time you get lucky, and so on. Now let's only talk about the cases where you get unlucky, right? Because that is the point where you lose the increments in M. So assume that this is another point in time where you are getting unlucky, and suppose at this point of time you are cutting off Y from your array. Now you can see that in this bigger window we had already made some strong claims that since you got unlucky, you can prove that every element has frequency less than or equal to 3. So that is why nobody took charge when X went out of this window. So then if you are getting unlucky again, this means that in this remaining section, every element has frequency less than or equal to 2. And then what is the next point where you will get unlucky? Suppose this is the cut where you will get unlucky. So if this is the point where you will get unlucky, you can now make a strong claim that every element in this region will have frequency less than or equal to 1. This means that frequency is equal to 1. This means that after this point, it is not possible to get unlucky anymore. And that is where the intuition comes from, that even if you did not know about that outrageous proof that I just showed you, that outrageous claim that said that if you start from n and if you reach n, right? I would say, even though this is also not that far-fetched, but still, like even if you did not come up with this observation that you have to cross every value to reach n, you could still have this deduction that the maximal frequency that you have, you can get unlucky if the maximal frequency is 5, then you can get unlucky only 5 times, no more than that, because the first time you get unlucky, it is guaranteed that nobody has frequency more, nobody has frequency 5 in this region. This means that everybody has frequency less than or equal to 4. And this time when you get unlucky, everybody has frequency less than equal to 3 and less than equal to 2 and less than equal to 1 and so on. So this means that after the last cut, even if your x has changed, then if you are indeed getting unlucky, you can only get unlucky maximum of 5 times, right? Because even if x changes, the maximal frequency cannot increase, and that is why your answer is this: k belongs to f to n. And this was the entire problem. So if you want to solve it, I will link down the problem in the YouTube description. Let me know if you had any other intuitive approach or easy approach to solve this problem, and let me know what do you think is the lead code or Codeforce's rating for this problem. Is it easy, medium, hard? Is it tricky? Is it obvious? What is it? Because a lot of in these kind of problems, hindsight is 2020. So a lot of people think that it's trivial. A lot of people think that it's very hard. A lot of people think that it's medium. Mixed opinions, and all of them are actually right in their own like area. Like all of the so there is no right or wrong answer to this problem in terms of difficulty, because if you see the solution, you'll say that it's very easy, it's obvious. But if you didn't spot the solution, you'll say that okay, it's a tricky observation based problem. Either way, do let me know in the comment section what you think about the difficulty of this problem.